Good morning, students. In this slide, we can see few devices, one diagnostic device and two sensors. There is something common in all types of automobile sensor like coolant sensor, speed sensor, fuel sensor, and also in some diagnostic appliances and oxygen sensor. In our last class, we discussed about magnetic field produced in a circular coil. We'll extend our discussion to know about something which is known as solenoid, which is used in all the above mentioned devices. Now, what is a solenoid? Solenoid is a long coil containing large number of closed turns of insulated copper wire, as you can see in the figure beside. Now, we can see that the two ends of the copper coil, it is connected to two terminals of a battery and it is passing through a switch. Switch is provided so that we can control the passage of current through the circuit, like we can make the circuit on and off. When current is passed through the solenoid, it produces a magnetic field around it. The presence of magnetic field can be detected by bringing any ferromagnetic substance like iron, nickel, cobalt or steel in the vicinity of the coil. It will be seen when the current is passing through the solenoid, those ferromagnetic substances are attracted towards the coil. This we have already seen in our microfile question number 3. We have experienced this. When the current is stopped, the iron substances will fall. It will not be attracted anymore. So the magnetic field produced by a current carrying solenoid is similar to the magnetic field produced by a bar magnet. The lines of force around the bar magnet we have done in our SAC class. It is always emerging from North Pole and entering and South Pole. And inside the bar magnet, they are parallel to each other. The same pattern is seen in solenoid also. Now, the magnetic field lines inside the solenoid are in the form of parallel straight lines. This indicates that the strength of the magnetic field is the same or uniform at all points inside the solenoid. So, the magnetic field is uniform inside the solenoid. One end of the current carrying solenoid acts like a north pole and the other end a south pole. So, if a current carrying solenoid is suspended freely, it will come to rest pointing in the north and south directions, just like freely suspended bar magnet. The current in each turn of a solenoid flows in the same direction, due to which the magnetic field produced by each turn of the solenoid adds up, giving a strong magnetic field inside the solenoid. Now we know that each turn of the solenoid behaves as a single circular loop. And in our previous session, we have already done and we have learned how will be the nature of the magnetic field produced around a circular loop carrying current. So, if many such circular loops are added together, which is seen in a solenoid, then each loop will produce a pattern like that and it will be added up and a strong magnetic field will be developed around the coils. Now, magnetic field lines of a solenoid. The magnetic field lines of a solenoid is similar to the magnetic field lines around a bar magnet. They always emerge from north pole and enter at south pole of a magnet outside the solenoid. And inside the solenoid, they are parallel and uniform. This diagram you need to practice. Remember, while drawing, you have to be careful about the two terminals of the battery, positive and negative. The longer side will be positive terminal and the shorter side will be negative terminal. Always the conventional current will pass from positive terminal to negative terminal. Accordingly, the arrow should be given. And remember, whenever you are showing an arrow for the passage of current, you have to show that the circuit key is closed, because current cannot pass through an open circuit. So, whenever you are putting an arrow from positive to negative terminal of the battery through the coil, remember the key should be closed. Now, after that, you have to specify north pole and south pole. After specifying the poles, you have to draw the lines of force. The pattern of the lines of force are known to us. And remember, always the arrows will be drawn from north pole to south pole. It will emerge from north pole and it will enter at south pole. What are the different ways in which the strength of a magnetic field produced by a current carrying solenoid can be increased? The strength of magnetic field produced by a current carrying solenoid depends on the number of turns in the solenoid. More is the number of turns, greater will be the magnetism produced. Second one is the strength of the current in the solenoid. Larger the current passed through the solenoid, more will be the strength of the magnetic field. The nature of the core material used in making the solenoid. The use of soft iron rod as a core in a solenoid produces the strongest magnetism. In the present slide, we can see different appliances shown. We can easily identify two things here. One is the electric bell and one is the electric generator. There are a few other devices shown. One is the sensor of train and one is a sensor of a signal. The strong magnetic field produced inside a current carrying solenoid can be used to magnetize a piece of magnetic material like soft iron when placed inside the solenoid as a core. The magnet thus formed is known as electromagnet. Here are some devices like electric bell, electric generator, electric signal system which uses electromagnet. Now we will discuss about electromagnet. An electric current can be used for making temporary magnets known as electromagnets. What is the working principle of an electromagnet? The electromagnet works on the principle of magnetic effect of current. That means when current is passed, magnetism is produced. Basically, the combination of a solenoid and a soft iron core is called an electromagnet. Thus, an electromagnet consists of a long coil of insulated copper wire which is wound on a soft iron core. But it acts as a magnet as long as the current is flowing in the solenoid. If you switch off the current in the solenoid, it no more behaves as a magnet. So it is a kind of temporary magnet. There can be different shapes of electromagnets as it is shown in the figure below. Now we'll discuss about the factors affecting the strength of an electromagnet. We have already discussed about the factors affecting the strength of a solenoid. More will be the number of turns in the coil, more will be the strength of an electromagnet. More is the current, more will be the strength. The third one is the length of the air gap between its poles. If you reduce the length of the air gap between the poles of an electromagnet, then its strength increases. For example, the air gap between the poles of a straight bar type electromagnet is quite large. So a bar type electromagnet is not very strong. On the other hand, the air gap between the poles of a U-shaped electromagnet is small. So it is very strong magnet. Both are seen in the diagram. Please note. Again, we are reinforcing the concept which we have developed in the previous slide, how to control the strength of an electromagnet. One way is by increasing the number of turns in the coil, and the other way is by increasing the strength of current. Both are shown in the diagram. Please note, because on this we will be doing some application based questions. Now, what is the difference between a bar magnet and an electromagnet? A bar magnet is always a permanent magnet, and an electromagnet is a temporary magnet. It exists as long as the current flows through the coil. So, magnetism of an electromagnet can be switched off and on as desired. The strength of a bar magnet cannot be altered. It cannot be increased or decreased for a particular bar magnet. But the strength of a particular electromagnet can be changed by altering either the number of turns in the coil, or by changing the strength of the coil, or by inserting or withdrawing a core material. Similarly, the polarity of the bar magnet cannot be altered. The north pole always remains north pole and the south pole always remains south pole. But the polarity of an electromagnet can be altered by altering the direction of current. But how can we change the direction of current? By altering the polarity or the terminals of the battery connection, we can change the direction, because always the conventional current flows from positive terminal to negative terminal. If we change the terminals, automatically the direction of current will be changed, and at the same time the polarity of the electromagnet will also be changed. What are the applications of an electromagnet? Electromagnets are very widely used in electric and electromechanical devices like motors, generators, transformers, electric bells, loudspeakers, phones, and in magnetic recording equipments like tape recorders, VCRs, hard disks. It is also used in medical technologies like MRI machines. It has its application in scientific equipments also, like mass spectrometers, particle accelerators, magnetic locks, etc. One of the main uses of an electromagnet, and it's the most common use also, in separation of magnetic substances from non-magnetic one. For lifting and transporting large masses of iron scrap, girders, etc., electromagnets are used. It is shown in the figure also. Here is one critical thinking question on the topic. We know that a solenoid is a long insulated copper wire which has many turns, and the two ends of which is connected to a battery through a switch. When current is passed through it, it behaves as a magnet. But when we are inserting a core material like soft iron inside it, it is behaving like a stronger magnet. Now, what will happen when a steel core is inserted in a solenoid instead of soft iron? Because we know that soft iron gives a stronger magnetism, but instead of soft iron, if we put a steel core, what will happen? We know that electromagnet is a temporary magnet. It exists as long as the current flows through the circuit. So magnetism of an electromagnet can be switched off and on as desired. This is actually an advantage of an electromagnet. we can use it according to our requirement. That is why core of an electromagnet must be soft iron, because soft iron loses all of its magnetism when the current in the coil is switched off. But instead of soft iron, if we put steel as a core material in an electromagnet, the steel does not lose all its magnetism when the current is stopped. It keeps a residual magnetism in it. So it becomes a permanent magnet. So with the same arrangement, if we put soft iron, it gives us a temporary magnet or an electromagnet. But if we put steel, it will turn into a permanent magnet. Now, which materials are used for making a bar magnet? Alloys like carbon steel, chromium steel, cobalt steel, tungsten steel, and alnico, which is an alloy of aluminum, nickel, cobalt, and iron, they are used for making strong bar magnets. We have already done experiential learning on the electromagnet and the properties of an electromagnet in our My Profile question number 3. I think you have enjoyed the session. Thank you so much. The learning outcome at the end of this chapter will be: the students will be able to know about the features of a solenoid. They will be able to draw the pattern of magnetic field lines around the solenoid. They will be able to know the factors affecting the strength of a solenoid. They will be able to know about the process of transforming a solenoid into a strong electromagnet. They will be able to differentiate between a bar magnet and an electromagnet. They will also be able to know the applications of electromagnet in various electromechanical devices. They will also be knowing about the advantages of an electromagnet over a bar magnet.